Okay, I'm just gonna click record what people think. Okay. Yeah, so any homework questions that people would like to go over? Well, right now I'm gonna go look to see how many people have even attempted the homework at this point. So don't mind me while I load that. Let's see how many people have started the first so many assignments. Okay. About half of you have done the demo, and a majority of you have started 1.1. Okay, that's cool. So conceivably you could have questions. So I'll just give you another moment or two if you decide to ask any questions. Okay, that's cool. Okay, well then we'll just start with material. Let me switch over to that mode. Okay. Boom. Okay, so we left off yesterday. Let's just sort of scroll up here and see what we did to remind ourselves. So we started a new section. Oh yeah, the calculus of parametric curves. So we started with, we had this idea, we had a parametric curve, we want to find the slope of the tangent line. So in other words, we're dealing with a derivative. And the first way that we found the slope of a tangent line was first we transformed the parametric equation into a rectangular equation. In other words, we eliminated the parameter. And here's like an example where we did that. It was sort of tedious to do this, but then we were able to figure out that there was a quick formula involving the parametric equations that we could use, right? And we just answered some homework questions about this. So we did a bunch of examples like that. I showed you how to use Wolfram to to have it graph for you, and I just showed you how I would paste it in there. Okay, so we did that. We talked about a second derivative formula. Okay, then we moved on to integration. Sorry, my ear itches. We moved on to integration, finding the area under a curve, talking about it in particular from the rectangular perspective. And we know that integration finds that for you. Then we talked about, well, what about if you want to find the area between a curve and the x-axis for a parametric equation? I showed you a formula for that. We did an example. Oh, I remember this. I messed up the fact that you're supposed to plug in the t values, the parameter values when you integrate. Okay, I remember that. Okay, then we stopped at arc length. There we go. That's where we stopped. So let's pick up from there. Let me make a little space. So I talked about what arc length is. So if you have a parametric curve, like what we have in blue right here, you have, let's say, your starting point and your ending point. So there's your start and there's your end. I think I need to zoom in a little. At 300%, yeah, that's 300%. So you start here, you end here. A point travels along the curve. It's parameterized. It starts at the start point and moves along, going like boom, 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 and like drawing some little dots so you can sort of see it like following the curve. So arc length is when we're interested in figuring out what the distance traveled by that point was. And there's two different formulas that we use. And I guess you should remember that whenever the s variable always refers to arc length. So if you ever see s equals something, chances are they're probably talking about arc length. Okay, and I gave you these two different formulas. They're both integration formulas. You'll integrate from a to b, where a and b are the bounds on the parameter, right? So you have x of t and y of t. T goes from a to b. So you can integrate the square root of the first derivative of the x parameter squared plus the first derivative of the y parameter squared. Or alternatively, you can integrate from a to b the square root of 1 plus dy dx squared. Okay, both of them will give you the arc length, the distance that the thing traveled. Okay, so let's use this to calculate something. So I'm looking for, this is a good one. So example type. Example. Let's calculate the, oops, I can't spell calculate. Let's calculate the arc length of a semicircle with radius 3, which is parameterized so that it travels counterclockwise. Okay. So notice I'm not even giving you the equations here. You're having to figure them out. But I give you a nice little description of what we're dealing with. So we're dealing with a semicircle. Oops, I didn't write in radius 3. There we go. The semicircle has radius 3, and we know it's parameterized so that the point travels counterclockwise. So let's like draw the picture of what we got here. Let's put in ourselves a XY axis. Okay, that didn't work. Okay, what's wrong with my XY axis? Okay, what the heck? I'm sorry, I'm having like, it's like not going in there. Okay, there we go. I don't know what was wrong. Yay. Okay, so whatever this is, it has a radius of 3, so it's gonna start right here at 3, 0. It's the semicircle, and it moves counterclockwise, so it's gonna go like this as it moves around. So remember, a semicircle means that it's half of a circle, so it's going to end up here at negative 3, 0, traveling like so. Okay, right? So you have your start, you have your end point. We want to figure out, as this point moves from the start point to the end point, how far does it travel? Now, this is a nice example because we already know what this distance is going to be. So without using calculus or parametric equations, how would we figure out what the distance traveled is going to be? Let's start off real easy. Wait, did someone say something? Adding what? Well, no, because it's going to move along this path. Yeah, there we go. Because you're moving along a circle, right? We know that the circumference of a circle is 2 pi r, so we know that the distance traveled s is going to be half of that. 2's will cancel. We know that we're going to get, the radius is 3, so we know it's going to be 3 pi. So what's nice about this example is that we already know what we're supposed to get. We're going to see if the equation I gave you actually gives that to us. Does that make sense to everyone? That's like why I'm going over this one first. Okay, so let's set this up. So to set this up, what we first need to figure out is the parametric equations. So if you look back in your notes, I showed you examples of parameterizing a circle. What were... Oops. Okay.
It's not letting me type.
What were the x and y parameters to get a circle? This is actually really important because you're going to be using this a lot. So eventually you're going to remember like the parametric representations of like a bunch of different curves. In particular, the circle. Say that again. I heard part of it. Yeah, right. So, but remember that for cosine and so which one was which? Like where did cosine go? X or y? Okay, x is cos and y is sine. But that's not quite correct because this was actually a circle of radius 1. We're dealing with a circle of radius 3. So I showed you an example. Yeah. Yes, exactly. So just to remember, you're always going to have x as cosine and y as sine, and then the number you put in front of them is always going to be whatever radius you need. So it's like really easy to set up a circle. And this is also parameterized so that it goes counterclockwise. The natural parameterization is counterclockwise, not clockwise. Okay, cool. So we have our parameters. Okay, now we got to use the formula. So let's change color. So step 2 would be plug into the formula. So we know that arc length. Oh, actually, we need to choose the parameter. We didn't do that. So the whole circle was from what to what? What were the values for t to get the whole circle? Do you remember? That gives the -3 and 3 gives you the radius. You have to think back to sine and cosine, and I don't remember who said it. I think it was Roger. But a whole period of pi is 0 to 2 pi. But 0 to 2 pi would give you the whole circle, so you only want half of the circle. So you're going to go from 0 to what? Yeah, pi. And you could verify that by plugging them in. You could plug in t equals pi. And you would get, so for the x value, you'd get 3 cosine pi. What's 3 cosine pi equal to? What's the cosine of pi? Yep, so you get -3. And then for y, you get 3 sine pi, which will give you 0, right? That gives you that point right there. Okay, this 0 to pi is really important because the formula says you're going to integrate from a to b, and this is your a, and this is your b, so you're going to integrate from 0 to pi, square root of 1 plus dy dx quantity squared. So we're going to need to figure out what dy dx is, but we have a formula for that. It's y prime t over x prime t, right? So we can go and we can plug that in. If you take the derivative of y, you get 3 derivative of sine is cosine. You take the derivative of x, derivative of cosine is minus sine. Okay. So the 3 and the -3 will cancel. You'll get minus cotangent. Okay, so you can now plug that into here. Make some space. Oops. Okay, so let's plug that in. So we're going to integrate from 0 to pi 1 plus, you're going to have minus cotangent squared, so it's going to be just plus cotangent squared of t. Oh, and this is supposed to be dt, not dx. Oof. Do we remember the antiderivative for that? Going and trying to find my antiderivative table because I do not remember what this is off the top of my head or if it exists. Okay, so 1 second. This would be like in the techniques of integration section. You know how there's like that big list of antiderivatives? I'm just like trying to find that right now to figure out what the antiderivative of this would be. Yeah. And I'm like, oh, holy crap, what the hell is it? Okay, I'm gonna Google list of integration formulas. Because we have square root of 1 plus cosine squared, or cotangent squared. They have 1 over 1 plus cotangent. Okay, so I'm not finding a nice formula for this. Maybe on this one. Maybe on this one. Let's see. No. What about this one? That's a derivative formula. Yeah, this is not really working out. Okay, luckily, there are 2 different formulas. We're not really making progress on this one, so let's see if the other one will be easier for us. That's usually what happens with these questions. You try one, and if you don't recognize it, you just move on to the other one. So remember that there's a second formula. Let's do this in green now. That will integrate from a to b, so 0 to pi. And it's the square root of, so then you do y prime squared. So we'll have 3 cosine t quantity squared plus x prime squared. So minus 3 sine t squared dt. And I think this one will be easier because when you multiply that out, it looks like this one was the better formula to use in this case. You'll get the square root of 9 cosine squared t plus, let's extend that a little, 9 sine squared t dt. And then notice this is not going to be that bad. You could factor out this 9 from both of those, right? So you get square root of 9, which is 3. You could put the 3 out in front. And then what are you left with? Cosine squared t and sine squared t. What can you just replace that with? Yeah. So this one actually ended up being easier. There's 2 versions of the formula because in different cases, like one might work more, you know, it might be a better case for what you're dealing with. So it looks like in this case, there's just this was the better formula. So I mean, like all of this just goes away. It becomes 1. And you get 3 integrate from 0 to pi dt, which means you get 3 pi minus 0, which gives you, oh my god, 3 pi, which is exactly what we said earlier. Alright, so it gives you the same exact answer that we got when we knew that we were just doing the top half of the circle. Okay, you have to be careful with these problems. Sometimes you might have to like try both of the versions. The other one didn't really pan out for us, right? We looked at it and we're like, oh man, I have no idea what the antiderivative of that is, or yeah, the antiderivative. But this ended up canceling really nicely. Yes, I am. I boiled the water in it for the tea. Mm-hmm. Mm-hmm. Right here? Yeah, originally I'd put a dx right here. That was a mistake. Oh, right here, but not right there. I see, yes. Yeah, this was a mistake right here. That should be dt. No problem. Yeah, both of them are dt. Or wait. No, yeah, that's dt. Because when you plug it in, you'll get a t here. Okay. Alright, cool. So, let's see. Should we do another one? Okay, so we did that one. Oh, okay. So yeah, let's do one more. Let me scroll down. Add some space. These end up getting used in physics a lot. So obviously we didn't need to use calculus to do this problem because we were able to calculate the area of a semicircle. So if you know anything about like throwing projectiles like around, like what shape do they usually travel? Like on the Earth? Yeah, right. But the arc is what sort of shape? Like, what do we know? Which? No, actually, no. Yeah, a parabola. So, like, for a lot of questions, you'll have something like, let's put example. You know, you throw a baseball and it travels, okay, I can't type, along the path below, and the path will be, okay, whatever, we'll just leave the x as uppercase. X of t might be, you know, something like 3t squared. Y of t might be 2t cubed. And, you know, the t values go from 1 to 3. What is the distance traveled? Okay, so this ends up being really useful for all sorts of like actual physical stuff. Okay, because, you know, we don't have any simple formulas to calculate lengths along parabolas and stuff like that. We have formulas, you know, for straight line segments, for squares, rectangles, and for semicircles, but we don't have an easy formula to refer to give us the answer for this one. So let's just do one where like this would work out, where you would need to do something like this. So let's see if we can we'll use the formula that panned out last time. We'll integrate from, oh, sure. Like that? Oh, up, you mean? Is that better? Cool. Wait, what time do we end today? Oh, okay. Actually, I'm going to nix this example because I want to get on to the next thing. I realize we have a lot to cover. Okay. We're going to move on to talking about polar coordinates. I just want to be able to talk about this. Okay, let me set this up. 300. Paper. Okay, cool. Okay, so you know how I've been talking about rectangular equations? Rectangular equations are so named because they come from the rectangular coordinate system. All right, so you have your x and y variables, and they go along with your x and y coordinate axis. And the name actually makes sense when you draw the picture. So for instance, let's look at the point 3, 0. Or no, sorry, 3, 2. So here is the point 3, 2. How did we actually get to this point? Well, we started at the origin, 0, 0, and we traveled along first the x-axis, like this, right here to 3, 0. And then we traveled up along the y-axis and ended up at the point 3, 2. Or alternatively, you could start at the origin 0, 0, travel upwards to 0, 2, and then travel right to 3, 2. Either way, whenever you trace out this path, what sort of shape do you end up with? So obviously you get a rectangle, right? You get this rectangle here, which is why it's called the rectangular coordinates. So there are other ways to come up with coordinates, and we're going to discuss them. One that we use a lot is polar coordinates. Okay, so let's talk about polar coordinates. So for rectangular coordinates, we have x and y variables. For polar coordinates, the variables we're going to have are r and theta. Okay, and we're going to work with them on the x and y coordinate system. So there's two different ways you can think about this. You can translate them to the x and y coordinate system, or you could think about having a r axis and a theta axis. Okay, so if we're talking about polar coordinates, the r and theta variables in the rectangular coordinate system, they have a particular meaning. Let me draw my x and y axis different. I want to draw it like this. It'd be easier to look at if I draw like this. So x, y. Okay, so the r stands for the radius, which is the distance from the origin. So if I say that r equals 3, I could be talking about a lot of different points, right? Does that make sense? You could draw a circle, and any of the points on that circle are a distance of 3 from the origin, right? We haven't really specified exactly what point we're talking about. So how is it that you specify one of these particular points? Well, you have to talk about a theta, and theta refers to the angular rotation from this line segment right here on the x-axis. So let's say, I don't know what I want to call that, from, let's just say the origin. So if I specify theta equals pi over 4, I'm saying, hey, normally we are right here at 0 degrees. Let's rotate up pi over 4 degrees, and now I'm talking about this point right there. So this point right here is, if we're talking about polar coordinates, it's 3, pi over 4. Now obviously that doesn't make a lot of sense on the x and y axis. We're going to have to translate it. Okay. Oh, that's what I'm saying. These coordinates right here, this is my coordinates r comma theta. That's why I was saying that those numbers don't make sense when you think about them on the x and y axis. We're going to have to translate them to an x and y point. So this is how I would refer to this point in polar coordinates. Okay, so when we talk about polar coordinates, we get two numbers, an r number and a theta number. Okay, that will give you a point on the x and y axis. We're going to have to translate it to this, like actual x and y values. Does that answer that question? So the 3 is not an x value, the pi over 4 is not a y value. What do you mean? Oh, yeah. So we're going to talk about exactly those formulas in a second. Yes. So the translation is not that bad. It just takes a little bit of trigonometry to figure it out. Let's draw an x and y axis. Oops, let me do that in white. Okay, so we always start here and we're going to rotate up by theta. Okay, and we end up with this point r comma theta. You could think of it like it swings like this. So we already know that this line segment right here is r. Let's move this. Have that be like right there. So you can see that you get a right triangle if you drop altitude right here. Okay, so this distance right here is the x value we're looking for, and this distance right here is the y value we're looking for. Okay, so we know if you were to set this triangle up and solve, you know that this x distance is r cosine theta. You know that this y distance right here is r sine theta. Did I say those backwards? X equals r cosine theta, y equals r sine theta. Okay, so for this example up here, the actual x value is 3 cosine pi over 4. The y value is 3 sine of pi over 4, which is 3 times root 2 over 2, and 3 times root 2 over 2. So this point right here, its x and y values are these. Does everyone remember doing this sort of stuff in trigonometry? Where you know like the hypotenuse of a circle, you know the angle that you know the hypotenuse of a triangle, and you know that one angle in the bottom left corner. Do I need to say more about this, or is everyone comfortable with that? Okay, cool. So this set of equations allows you to figure out the rectangular coordinates from the polar coordinates. So you're taking polar and you're spitting out rectangular. You also need to go the other way. There's a set of equations to go the other way. So r squared, or let's just say r, if you want to figure out the r value, that is going to be the square root of x squared plus y squared, and that's actually makes a lot of sense when you realize that if the bases of your the base and the height of your triangle are x and y, you can solve for the hypotenuse, and this is what you would get. And theta is going to be equal to the tan inverse of y over x. And that makes sense because if you're solving for that theta right there, right, y over x is the tangent ratio, right? So you would do the tan inverse of that. So this is how you would go from having rectangular coordinates to polar coordinates. Questions so far? Just gonna pause for a moment. Okay. Vectors, let me look. I think that will be next class. Yeah, we'll get to vectors later. We're not going to get to vectors for a little while. We're going to spend a bunch of time on polar coordinates before we move on to vectors. Okay. So let me scroll down. Now we get to talk about equations and their graphs in polar coordinates. Okay, so you know how to work with a rectangular equation. Like, you know how to take y equals x squared plus 3 and then turn that into a graph. So how does that work for polar coordinates? So for polar coordinates, instead of using the x and y variable, you're going to use the r and the theta variables. Okay, so an example of a polar coordinate equation would be r is equal to 4 sine theta. Okay, so let's identify the curve and translate to rectangular. And translate to a rectangular equation. Or translate to rectangular coordinates. So when starting off with these, it's best to usually make a table of values, and you sort of have to think about this. So notice we have a sine. What do we know about sine? Like, as a function, what do we know about it? It has some nice properties that will help us out here. What do we know about sine? What are things that we know? Like, it will narrow down like the sorts of numbers that we have to plug in. Any ideas? What do we know about sine? Sine, cosine, and most trig functions. Like, what do we know about their graphs? Yeah. So they oscillate, but more importantly, when you say fixed numbers, we know that they're periodic. Which means that we only really need to plug in numbers between 0 and 2 pi. right? There's no point in plugging in 3 pi because it's going to give you the same number as pi. So we can take theta values. And we'll plug in numbers like 0, pi over 4. Let's plug in some simple ones. Pi over 2, pi. Let's plug in also, what else should we plug in? We'll also plug in, yeah, we'll plug in that. We'll see what we get. We can plug in some more afterwards. So we're going to plug that into 4 sine theta, which will give us our r value. Okay, so what's the sine of 0? Sine of 0 is 0. 4 times 0 is 0. Okay, the sine of pi over 4 is 2 pi. Oh my gosh. I'm like blinking for some reason. What is the sine of pi over 4? It's root 2 over 2, right? I feel like I'm like doubting myself all of a sudden. Yeah, it's root 2 over 2. Okay, then we're multiplying by 4, so the 4 and the 2 will cancel and we'll get 2 root 2. The sine of pi over 2 is 1, so we're going to get 4. Sine of pi is 0. Cool. So let's go and like plot those. Let's see how this will work out. So the theta equals 0 means that we're going to lie along right here where the angle is 0. And how far away from 0 are we going to travel? 0. Okay. Now, moving on to the next value, our angle is pi over 4. And how far away from pi over 4 are we going to travel out? Root 2 over 2. And that's approximately 2.8. So let's just measure this out. Our 1 will be like right here. So 2.8 would travel out to like approximately right there. Okay. Then you can look at pi over 2. You're rotating up to pi over 2. Because remember 4 sine theta gives you the r value. That tells you how far you're going to travel out. So you travel out 1, 2, 3, 4. So you get a point like right there. Let me put those in red so we can see them a little better. Okay. Next one, we're rotating out pi. That's over here. And let me mark these. So this is theta equals 0. Theta equals pi over 4. Theta equals pi over 2. This one is theta equals pi. How far are we traveling? 0. That puts us back at this point right here. Because we're not moving in that direction. So let's add in some more numbers. Maybe we should add in this one, which would be theta equals 3 pi over 4. Okay, what's the sine of 3 pi over 4? It's going to be also root 2 over 2, so this will give us 2 root 2. So you would also travel out 2.8. So you get like a point like right here. Let's plug in some different numbers. Maybe pi over 6. 30 degrees. So pi over 6 would be like right here approximately. Okay, what's the sine of pi over 6? What do we get? What is the sine of pi over 6? Can't remember off the top of my head. It's the sine of 30 degrees. I want to say it's 1/2. Okay, cool. So you get 4 times 1/2, you'll get 2. Okay, so you're going to travel out 2. Okay, then you'll also get the same thing over here. So you get like a point right here. So you get this point. So you get these, how many points do I have so far? 1, 2, 3, 4, 5, 6 points. If you were to keep filling these in, you would eventually see that you get this circle shape. I think it actually is a circle. So if you were to keep on filling in points, you would see that you'd get that. And let's talk about how you would know that. And that will involve translating to the rectangular coordinates. So what we're going to do is we're going to, let's see how we're going to do this. 1 second. We're going to give you those equations I gave earlier, but I want to do this in the right order. So I told you that r equals the square root of x squared plus y squared. Let's square both sides of this equation. And we're going to get r squared equals x squared plus y squared. Okay, and the equation I worked on this all with earlier was we knew that r was equal to 4 sine theta, correct? Which means what is r squared equal to? Actually, wait, no, that's not what I wanted to. Okay, let's make sure we do this right. So this is the equation that we started with. Okay, wait, I'm messing something up. 1 second. Oh. Here I have r squared equals x squared plus y squared. This is just r. I would like to be able to set those equal to each other, so I'm going to square both sides of this. So if you square both sides, you get r squared, or sorry, not square both sides, multiply both sides by r. That's where I keep on messing up. I keep on saying like I'm going to square, but then I'm like, wait, no. So let's multiply both sides by r. That's going to give us r squared equals 4r sine theta. Okay, now we can set those two equal to each other. So I'll replace the r squared with 4r sine theta, and we know that that's equal to x squared plus y squared. Okay. And let's, there's some more equations we were given. We know that r squared equals x squared plus y squared. What were the equations for x and y that I gave you earlier for polar coordinates? So what were the x? Thank you. And what's y equal to? Awesome. Okay, so we can start making some replacements here. Y is equal to r sine theta, and you see that in this equation right here. So this can just become 4y. So to do these problems, normally what you want to end up with something that just has rectangular equations. So what you're going to do is take those equations that I gave you earlier, sort of rejigger them around. Usually you're going to know what r is equal to, so you'll make a replacement. You know, this is how we plugged in. We were able to take this equation and this equation. We got an equation which had both rectangular and polar coordinates. And then we want to end up with something that has only one. Okay, and so we have this, and then we can actually figure out that it's a circle. We could we could put it into standard form. So what could we do? We could move everything to one side. I would rewrite this as x squared plus y squared minus 4y equals 0. Okay. So we would split these up. I need to complete the square on this. Let's see, I haven't completed the square for a while. And when you complete the square, you need to take the negative 4, you divide that by 2 and you square it. All right, so negative 2 squared is 4, so I would add 4 to both sides. So y squared minus 4y plus 4 equals 4. And then this would factor now, so this is x minus 0 squared plus y minus 2 squared equals 2 squared. So looking at this, you can see that it's a circle. And what is the center? Looking at the standard equation. Yeah? Yeah, 0, 2. And then what's the radius? Exactly. And if we scroll back up, you can see that here at 0, 2 is approximately the center, and it moves 2 in each direction. Okay. So usually when you're starting off with this sort of stuff, I highly recommend that you plug in different values, you plot them, you try to connect the dots, and then to verify the shape that you get, if it's any recognizable shape. Usually it's a little complicated, but you're going to use the equations that I gave you earlier, right? Like x equals r sine theta, x equals r cosine theta, y equals r sine theta, the fact that r squared equals x squared plus y squared. Use the polar equation that they gave you, substitute it in, get something which has a mix of both, keep on making replacements until you get something that just has rectangular coordinates, then put it into some sort of standard form. Okay. I think we're just going to end here. It's the end of the first week. I sort of feel the mental drain on me right now. So hopefully you're feeling good. Before you go, please sign in on the chat.